Okay, welcome to the operations research course. So for today, we will look at linear programming. So we'll go through a brief introduction of linear programming, what's linear programming in general. Then we will zoom into model formulation. How do we formulate any particular model? Then we'll solve linear programming problems. We would look at the simplest method of solving linear programming methods. Then we'll look at the two-phase simplex method for solving linear programming problems. So let's look at what do you mean by linear programming? So linear programming is the best known or one of the most widely used techniques of operations research. Some people also refer to operation research as management science or engineering science. So linear programming is actually a mathematical method which involves allocation of scarce resources to competing activities in the best possible way. Usually, we refer to the best possible way as optimal way or the optimum allocation. We will look into that and we'll see that sometimes the best is not optimal. So the right word is the optimal solution or optimal way or the optimum allocation of resources. So linear programming is very widely applied in several sectors, in engineering, in the health sector, in government sector, the military, and also the various industries. So in mining, linear programming has been applied in the following areas: transportation of materials, assignment and or allocation of machines to each other, maybe truck allocation to shovels, or perhaps how we transport materials from various mining sectors to the ports to ensure that we have maximum output or maximum net present value or maximum revenue in general. It has been used in production planning. It has been used in scheduling and also finding optimum production process. Linear programming has been used in blending problems or product blending, where we try to combine products to achieve maximum output or revenue, and location of facilities, or how do we site facilities. If you have several producing centers and you want to site a particular facility that depends on the various producing sectors, linear programming finds useful in those areas. Also, you have several investment opportunities and you want to invest. Linear programming has been used to find the best investment opportunity to use and also analyze investment. So there is a wide range of the application of linear programming. Now, how then do we formulate any particular problem? So usually, once the problem has been identified and we realize that we can apply linear programming, the next step in solving the real world problem, which usually we say is unstructured, is formulation of a mathematical model or structuring the real world problem in mathematical way. Now, sometimes or in the real world, the problem will be identified, but we must then create the problem and then try to solve the problem using linear programs. So when I say you create the problem, I mean that we define the particular problem in a well-structured way that could be formulated by mathematical methods. Now, three ways are involved when we are formulating mathematical model. The first one is the identification of the decision variables. When we say decision variables, what we mean is that what are the things that we required to know after the problem is solved. When we identify the problem and we want to solve the problem, what are the things that we need to find out to be able to say that after managing these decisions or these variables, then it means that the problem has been solved, or it can help us solve the problem. That's what we call decision variables. So we need to first identify the variables that are dictating the decisions to be made after solving the problem. Then we develop an objective function. An objective function is usually the linear relationship of the decision variables. So we find, because it's linear programming, we find a linear relationship between the decision variables that will result in the final ultimate goal of solving the problem. Like for instance, that will result in finding the NPV of a particular project, finding the revenue of a particular project, finding the cost of a particular project, finding the times of a particular problem. So when that is done, then we determine the constraints in the system, or we determine the restrictions in the system. So the restrictions in the system is also linear. Remember, we are doing linear programming. So it's the linear relationship of the decision variables that reflects the limited resources of the problem. The limited resource of the problem. So what we'll do now is to take some problems and walk through them and see how we would appreciate the formulation of linear programming problems, and perhaps we can solve some of them. So this is a typical problem. So a manufacturing company wishes to determine how many of each three different products, how many of each three different products they should produce given the limited resources to maximize total profit. Now the labor, the material requirements, and the contribution to profit for each of the three products are as follows. So there are 240 hours of labor available daily for production. The company is limited to 400 kilograms per day. The company wants to determine the quantity of each product to produce to maximize the profits. So now, our problem here is to formulate the problem as a linear programming tool. So to find or to put all these write-up or these written statements into a tabular form. So we'll represent product 1, product 2, product 3 on this table. We have the resource labor, which is hours per unit. Remember, it's 240 hours in total. And we also have the requirements material, or the material required. So these are product given and profits for selling each particular product, or the profit for derived after that product is sold. So for product 1, we are saying that it actually requires 5 hours. If you want to produce 1 unit of product 1, you need 5 hours. You need 4 kilograms of the material. And when we sell it, we'll have $3 per unit. For product 2, it requires 2 hours of labor, 6 kilograms of material, and $5 of profit when we sell them. Then for product 3, we have 4 hours of labor, 3 kilograms of materials, and when we sell it, we are going to generate $2 per unit. So this is what we will do. I would bring out my I'll bring out my dashboard so that we can work on this. All right. So that we can work on this. So this is the dashboard that I'll be using. I think blue, I like the color blue, so let's use that. All right, and let's see what we have here. So usually, right, the first thing, as we said, is the decision variables. So we identify the decision variables. Remember that we are dealing with 3 products and we need to find out each of the 3 products that should be produced, right? So the decision variables will actually be the quantity of product 1 that needs to be produced on a daily basis, the quantity of product 2 that needs to be produced on a daily basis, and quantity of product 3 that needs to be produced on a daily basis. So what we say that the decision variables is usually X. Let's use X to represent the quantity of material. That's the products. And let's use 1 to represent product 1. So we are saying that X1 is usually the quantity of product 1 produced per day, right? Then also we have product 2. So X2 is also the quantity of product 2 that must be produced per day. Then we have X3, which is also the quantity of product 3 produced per day. So you see that there is a trend here. So what then we will say is that let Xi, right, be the quantity of products I produced per day. So this is then the decision variables. All right. Now the second thing to do is to find the objective function. So to find the objective function. All right. So remember that we said the objective function is the linear relationship between the decision variables, right? So the objective function here is to maximize the total profit. Because the question is that how many of each of the 3 different products should be produced, given limited resources, to maximize total profit. So usually, or what we are looking at here is the total profit. And we know the profit from each product, right? So we know the profit for each product. So the profit for product 1 is 3 per unit. The profit for product 2 is 5, and that for product 3 is 2. So the linear relationship between them is that for me to maximize the total profit, right, then we will say that we should let Z, right, represent the total profit. If that's the case, then we will say that our problem is to maximize the Z. So maximizing the Z is related to the three products. What are they? The product one, what is the profit? Is 3. However, the total profits for selling product one is 3 times the quantity of product one that must be produced in a particular day, right? That will give us the total profit. Again, that of product two, the profit is 5 per unit. So therefore is 5 times the X2, right? Which is this one. Then the final one will be the third one. And what is the product here is 2 times X3. So this is the objective function, right? We can just make it max Z is 3x1 plus 5x2 plus 2x3. So the first thing to do is to find the decision variable. The second thing is to determine the objective function. And the third is to determine the system constraints. So the third is to determine the system constraints. So we'll have the system constraints. How do we determine these system constraints? All right, so everything has been provided in the problem. The first one is we have the labor constraints. So the labor constraint says that for product one, we can only produce, or we can use 5 hours of labor per unit. If we want to produce one of product one, we need to use 5 hours of labor. If we need 1 unit of product two, then we need 2 hours of labor. Then if we need 1 unit of product three, we also need 4 hours of labor. So what we do is that we also find the linear relationship between the constraints. Remember, that is what is said, right? However, the total labor available to us is 240 hours per day. And remember, all the formulation has been done per day, right? So we have the quantity of product one produced per day, quantity of product two produced per day, quantity of product three produced per day. And the objective function is also the total profit per day, right? The total profit per day. So when you are also defining the constraints, we have to also bring it on the same level of measurements, right, which is per day. And therefore, this is what we'll do. We must then have the total labor constraint. The total labor constraint is that 5 hours per unit. But how many quantity of product one am I producing? I don't know. So it's represented by X1. Remember, decision variables, we don't know. Plus, so I have to add the hours to product 2. That's how many hours am I producing for product 2. For that one too, I don't know, but I know that labor 2 is spending 2 hours per unit. So the 2 hours multiplied by the total number of units produced, or total number of products 2 produced, is x2, right? Then finally, the third product is 4 hours is being spent per unit, and I'm trying to produce how many quantity of product 3. So that is that, right? It's a constraint, meaning that the total hours for product 1, for product 2, and product 3 cannot be unlimited, right? We have 240 hours of labor available for us in a day. So it means that we can not exceed 240, though we can be equal to 240. So this is the first constraint, the labor constraint. Let's look at the second one, material constraints. So for material constraints, we were again given that for product 1, we need 4 kilograms of material to produce 1 unit. For product 2, we need 6 kilograms, and for product 3, we need 3. Therefore, what you do is that the total material needed to produce product 1 will be 4 times the decision variable x1. The total material needed for product 2 is the 5 kilograms per unit times the total product 2 that must be produced, which is x2. And similarly for product 3 is 2 times x3. Again, the company is limited to 400 kilograms per day, and therefore you cannot exceed the 400, but you can use all the available 400 in a particular day. So this one is again the constraints per day. Now, what do we have here? The company wants to determine, so the constraints which were given or which we know pertain to this problem, or we have identified. So in the real world, we are going to define our own constraints. So the constraints that we have identified are labor and material. However, we want to also ensure that we are not producing any negative decision variable. All our decision variable should be positive. That means that we have to constrain our decision variable. And if you want to constrain your decision variable, then it means that we should have what we call the non-negativity constraints. So non-negativity. So the non-negativity constraints is we don't want to produce x1 to be negative. So we'll say that x1 can be equal to 0, but should also be greater than 0. x2 can also be greater than 0 or equal to 0. Then x3 is also 0 or greater than 0. Now, what this one means is that we are telling the system that when we solve the problem, we don't want to obtain any negative value. Remember, x1, x2, x3, right, are being represented by xi. So we can say that is xi should be greater than or equal to 0. Right. So when you identify the problem like this, you are actually not finished, right? The final thing is to put this in mathematical model framework. So the mathematical model framework is presented as, I want to maximize my Z. So we'll say that maximize Z or max Z is 3x1 is 3x1 plus 5x2 plus 2x3 is subject to, what are the constraints? The labor 5x1 plus 2x2 plus 4x3, which is less than or equal to 240. Then the material is 4x1 plus 6x2 plus 3x3 less than or equal to 400. Then we have x1, x2, x3 is greater than or equal to 0. And this is what we call a mathematical model. This is what we call a mathematical model. All right, so for this lecture, we have looked at how to formulate a mathematical model using a typical example. All right, so we will look at another example. We'll look at another example. So let me close this whiteboard and share the screen. All right. All right. So this second example. A mining company operates 3 mines. The ore from each mine is separated into 2 grades before it is shipped. Now, the daily production capacities of the mines and their respective operating mines are shown in the table below. So, mine one is producing mine 1 is producing 4,000 tons of high grade ore per day. Mine 2 is producing 4,000 tons of low grade ore per day. And the operating cost is $1,000 per day. Mine 2 is producing 6,000 tons of ore, high grade ore per day, 4,000 tons of low grade ore per day, and the cost is 22,000 per day. So the first one was 20,000 a day, 22,000 per day. Then mine 3 is producing 1,000 tons of high grade ore per day, 6,000 tons of low grade ore per day, and operating cost 18. So given that the company has committed itself to deliver 54,000 tons of high grade and 65,000 tons of low grade ore in a given week. So in a given week, we now want to formulate a mathematical model to determine the number of days each mine should be operated in the week in question if the company is to fulfill the commitments of minimizing the total operating cost. So number of days, right? So you can see the previous one was products that are being produced per unit. right? However, in this particular time, we are looking at number of days. So you have 3 mines. These are typical mining problems, which also transcends to transportation problem, or it also transfers to transfers to other problems in a typical environment, right? So I'm trying to correlate this not only as a mining engineering problem, but also a problem for even the mechanical engineers in terms of how then should you allocate your machines or equipment to be able to achieve this particular framework or problem, right? To be able to achieve results. And or even the electrical environment, where should you focus your strength or your planning model to, or with each particular mine, right? So the mine are set up to do this. So again, we'll go back to our dash, our whiteboard, and solve this particular problem. All right. Okay. So we have this. So this is where we are the last time. So we'll create a new dashboard here, a whiteboard here, and I still prefer my blue. So we said 3 things, 3 steps. The first one is decision variable identification. The second one, objective function. And the third one, system constraint. So we need to remember this. So number 1, is our decision variables, right? Decision variables. Remember, the question is, or what we seek to do is to determine the number of days each mine should be operated. The number of days each mine should be operated. So again, here, we can just go straight and say that we have 3 mines. So let's xi, where I is equal to 1, 2, 3 mines, right? So let xi be the number of days, the number of days that the mine I is operated per week. So this is our decision variable. We want to find the number of days my I is producing or is operating per week, right? Then 2 is the objective function. So what is the objective function? It says that the company wants to fulfill its commitment at minimum total operating cost. That means that the objective function is to minimize the operating cost. We know the operating cost for each mine. In a typical environment, we might have determined or calculated or computed operating cost for that particular mine. Here, we've been provided with the operating cost for each particular mine. So that means that the objective function is to minimize the function. And we say that the function is represented here again with z, right? So we want to minimize the function, and it's a linear relationship between the decision variables, right? Now, the operating cost for my 1 is 20,000, and x1 is representing my 1. So we will say that 20,000 times x1 is the total operating cost for x1, right? Then we have 22,000 x2, then 18,000 per day. 18,000 x3. Right, 18,000 x3. Right? So the number of days we are producing in a particular week. So this is the objective function, right? Then the system constraint is so system constraint. What are the system constraints or the restrictions? Right, the first one is the low grade ore. Is the low grade ore. Yeah, is the low grade ore. Okay, yeah, we'll still use the low grade ore. We also have high grade ore. Then what again? The number of weeks. How many days do we have in a week? So number of days in a week, right? So for the low grade ore, constraints. Now, we are given that mine 1 can produce 4,000 tons of low grade ore in a particular day. Mine 2 is 4,000 low grade ore, and mine 3 is 6,000. So that means that the 4,000 low grade ore times the X1, that's the number of days we are producing, plus the 4,000 low grade ore that is being produced, 4,000 tons for mine 2, then 6,000 low grade ore that is being produced for mine 3, right? However, the total low grade ore per the plan, per the mining plan, is 65,000 tons per week. So it means that this is committed to deliver. So committed means that the minimum that they want to produce is 65,000 tons of low grade ore. That means that if they produce more than 65,000, it's a good thing for the mine. And therefore, it should be greater than or equal to 65,000. Why? Because the limit they are putting on themselves is 65,000. So that means that the minimum should be equal to 65,000. They can produce more, which is greater than or equal to, which is greater than 65,000. That's why we say greater than or equal to 65,000. The second constraint is the high grade ore. 4,000 tons of high grade ore is being produced by mine 1. So 4,000 times the total days that are produced that mine 1 operates in a week, plus for mine 2, it's can do 6,000 tons in a day. So 6,000 tons in a day times the number of days that is being produced. Then mine 3 is 1,000, right? And again, the mine is committed to 54,000 tons of high grade ore. So it means that the mine wants to produce something which is greater than or equal to 54,000. Right. Then the third constraint is the number of operating days. per week. So the number of operating days per week, we have X1 can not be more than 7 days because we have 7 days in a week. All right. X2 can also let me do a vertical. Then X3. So all this could be Xi is less than or equal to 7 days. Right. Then our non-negativity rule, we also need that. So the non-negativity constraints, which is Xi should be greater than or equal to 0. So when this is formulated, remember you have to put it in a mathematical modeled framework, which is you want to minimize Z. Sample use S instead of Z, and it's 20,000 X1 plus 22,000, that's the cost for S2, mine 2, and 18,000 X3. Then we'll say that this one is subject to the low grade 4,000 X1 plus 4,000 X2 plus 6,000 X3, and is greater than or equal to 54,000. Then the second constraint is a high grade 4,000 X1 plus 6,000 X2 plus 1,000 X3, which should also be greater than. So the first one is 54,000 is for the high grade, and 65,000 is for the low grade. Then we'll say that X1 is less than 7, X2 less than 7, X3 less than 7, and also X1, X2, X3 greater than or equal to 0. So usually all these must be aligned. So let's align them. Say X1, 7, X2, less than or equal to 7, X3 less than or equal to 7, then X1, X2, X3 greater than or equal to 0. That's the non-negativity rule. So this is it for this particular mining problem. All right. So thank you for attending to this lecture. So the next lecture or the next video will be double subscripted types of problems. A problem where it's a little bit more complex, but can be used for blending type of problems. or investment type of problems where we have different variations of the decision variables. So where a decision variable is a subset of the other, and we'll see how we can also formulate that. So thank you for joining this lecture, and we hope to meet again in our next lecture. All right, thank you. Bye-bye.